Okay, so we're asking the question, how does the neural network learn? And we said that we want to minimize the difference between the actual um, output, I'm sorry, the actual value, the target value, and the output of the neural network. And we want to do that for all of the, so we run through all of the records. Here we also say through all the output nodes, but usually we just have one output node. So we don't really have to talk about going through all the output nodes. But if we have more than one output node, we would have to do that over all the output nodes as well. The problem is therefore to construct a set of model weights that will minimize the SSE. And this way, the weights are analogous to the parameters of a regression model. The true values for the weights that will minimize the SSE are unknown. So we say that in statistics. We say that the true weights are unknown because we only have a set of data, or it's kind of a subset of all possible data. So we can't get the real data, the total data set, so we can't get the true weights, the actual weights, because that the actual weights means like for all possible data, but we only have a subset. And our task is to estimate them given the data. However, due to the nonlinear nature of the sigmoid functions permeating the network, there exists no closed form solution for minimizing SSE as exists for least squares regression. So in least squared regression, you can get what you're looking for, the parameters, given a set of data, but here you can't. So we turn to another method called the gradient descent method. We must therefore turn to optimization methods, specifically gradient descent methods, to help us find the set of weights that will minimize SSE. Suppose that we have a set vector of m weights in our neural network model. So remember we had the weights, so we'll just list them as a vector. And we wish to find the values for each of these weights that together minimize SSE. So we want to choose some set of weights that's going to minimize the SSE. Now, what does that mean? Going back to this picture, we could, these weights, all of these weights, W's, all these W's, originally they were randomly set, and then we're going to change them in some way. And we want to change them in a way so that when we run all the data, each record, all the records through this neural network, and we calculate that so-called SSE, we calculate basically how much error we got. We'd like to set the weights so that that error is least, is what we're saying. So going back, so here we're going to minimize SSE. We can use the gradient descent method, which gives us the direction that we should adjust the weights in order to decrease the SSE. The gradient of SSE with respect to the vector of weights W is the vector derivative, like this. So first of all, for those of you not that familiar with gradient, let's see, we're putting in a vector and we're getting out a vector. First of all, we can notice that. So the input is all the weights, which can be expressed as a vector of the weights. And what we get out, this is a vector. You can tell that it's a vector because it has these commas, comma, comma, comma. So that means you get a value here, something, whatever this is, and then value here, and so on and so on and so on. So that's a vector. So what is this vector? What is it? What is this resulting vector? So what's the first component of the vector? What's the second component of the vector? What's the last component of the vector? So the first component is, this is the derivative, or actually the partial derivative, of SSE, which we already talked about, with respect to a small change in the first weight. So in other words, how does the SSE change with respect to with respect to a change in the first weight, a small change, and how does SSE and this is holding all the other, when this is the partial derivative, right? So it means holding all the other weights constant and just changing W sub 0, and then holding all the other weights constant and just changing W sub 1, and so on. How does the SSE change? So this is called the gradient, and this will give you will give you a vector. We said it'll give you a vector, and so it will give you, if you think of it as a vector, it's a kind of direction in which to change the weights. So let's see. That is the vector of partial derivatives of SSE with respect to each of the weights. So this is a vector, and it will tell us, basically, as we'll explain in a minute, it's going to tell us how much to adjust each of our weights in order to get to reduce SSE. Okay. Okay. So let's say this again. So we're going to take the gradient of SSE of W, and this is what we get. Okay. To illustrate how the gradient descent works, let us consider the case where there is only a single weight, W1. So let's make it really simple. So instead of having many weights, suppose we just had one weight. Consider figure 4, which plots the error SSE against the range of values for W1. So remember that we said that we want to choose the weights so that we minimize SSE. So SSE depends on the weights, and so this figure plots the error, or the SSE, against the range of values for W1. So depending on what W1 is, you're going to get a different SSE, and that's shown here. So depending on the weight for W sub 1, if it's down here, if it's over here, it's over here, we expect SSE to vary. We would prefer values of W1 that would minimize SSE. The optimal value for W1 we'll call W1 star. We would like to develop a rule. So in other words, we start with a certain W1, right? All the weights are randomly assigned. And then we want to find some rule which will tell us how to adjust W1 in order to hopefully minimize the error. So we'd like to develop a rule that would help us move our current value of W1 closer to the optimal value, W1 star, as follows. The new one is the current plus some change in the current, where the change in the current is the change in the current location of W. But the real question is, we have no idea how to change the weights. Like you have a random weight. Now how should you change it to decrease SSE? You have really no idea. But the question is, what should delta W current be? And like, should it be positive or negative, and should it be big or small? We have no idea. Okay. Of course, if it looked like this, we have some idea. But we don't know the actual shape of this curve. Now suppose that our current weight, W sub current, is near W1 left. So suppose it's over here. Then we would like to increase our current weight to bring it closer to the optimal weight. So we want to increase to move it over this way. On the other hand, if our current weight is here, then we'd want to decrease. We'd want to bring it closer to the optimal value W sub 1 star. So what does the derivative have to do with that? Well, what's the derivative? If you're over here, what's the derivative? It's negative. And if you're over here, what's the derivative? It's positive. So do we want to move in the direction of the derivative? I mean, the derivative is negative. Do I want to add something negative to this? No. I want to add something positive, the opposite of the derivative. If I'm up here, the derivative is positive. Do I want to add something positive to this to get to here? No. I want to add something negative, so the opposite of the derivative here. Now the derivative is simply the slope of SSE at W1. For values of W sub 1 close to the left, the slope is negative, and for values of it close to the right one, the slope is positive. Hence the direction for adjusting W current is the negative of the sign of the derivative. That is, the negative of the sign of the derivative. This is the partial derivative, but it's still the derivative. How far should W current be adjusted in the direction of, in that direction? So, okay, we now know that we want to move in the opposite direction of the sign of the derivative. The sign of the derivative here is a negative. We want to move positive, so we want to move the opposite of negative, which is positive. Now, how much should we move? So if we're way over here, we want to move a lot, right? And notice the slope is steeper over here. So it means that the slope is greater over here. Well, on the other hand, if we're over here, the slope is not so great, and we don't want to move so much. So not only do we want to move in the opposite direction of the sign of the derivative, but the magnitude of the derivative gives us some idea of how much we want to move in that direction. So now how far should W sub current be adjusted in the direction of the negative of the sign of the derivative? Suppose that we use the magnitude of the derivative at W sub current. When the curve is steep, the adjustment will be large since the slope is greater in the magnitude of those points. When the curve is nearly flat, the adjustment will be small due to less slope. Okay, so we can use that idea. Finally, the derivative is multiplied by a positive constant, eta. It's called eta, called the learning rate. So like, this slope is great. So how much does that mean we should move to the right? Well, we said it means we should move kind of a lot to the right, but taking it exactly as the slope is kind of stupid. So why not? Because it's not exactly related. It's proportional to the slope, but not exactly related. So we multiply this times some learning constant. So if the learning constant is high, then we're going to take this slope and multiply by a large number, then we're going to move a lot. If the learning constant is small, then we're going to take this slope and multiply it by a small number and move less each time. Right? Each time. So that's called the learning constant. The resulting form of the change that we want is, the change is, we said negative, and then eta, and then the slope, meaning that the change in the current weight value equals negative a small constant times the slope of the error function at W current. Okay, let's stop here.